Okay, we are going to do some curve sketching now, but instead of looking at polynomial functions like we have for the past 2 days, we're going to start looking at rational functions. So the big difference that makes is we may not have a domain of all real numbers. We will probably have some asymptotes, both vertical and horizontal. So first thing we do want to do, though, like normal, is find the domain. So in a rational function, the problem I might run into is if my denominator is equal to 0, that would give me a vertical asymptote. In my first example here, my denominator is x squared plus 5. That can never equal 0 because I'm squaring a number and I'm adding 5. So actually in this rational function, my domain is still all real numbers. Okay? In behavior, this time we are not looking at a polynomial, so it's not the 4 options that we have based on the degree and the leading coefficient. Now we're looking at the degree of the numerator, which for us that degree is 2, and the degree of the denominator, which for us that degree is 2. And remember, when those degrees are equal, we have a horizontal asymptote that's y equal to the ratio of the leading coefficients. So we have a horizontal asymptote at y equals, this will be 1 because my coefficients are 1 over 1. So in the long run, our graph will level out at y equals 1. Okay, y-intercept, same thing. I want to plug in x equals 0, and when I do that, I get 0 over 5, which is 0. X-intercepts, if I have a rational function, to find the x-intercepts, I take my numerator and I set it equal to 0. So I would take x squared, set it equal to 0, and I just get 0, 0 again. Alright, so this is what I can get from the original function. Now I need to know, where is it increasing? Where is it decreasing? Do I have any maximums? Do I have any minimums? So I have to find the first derivative here. So finding the first derivative of this requires quotient rule. And if I look, derivative of the top is 2x. Derivative of the denominator is 2x. So my derivative, f prime of x, will equal low d high, so that's 2x times x squared plus 5, minus high d low, 2x times x squared, all over low squared, so the whole quantity of x squared plus 5 squared. Now if I take that numerator and I multiply it out, so keep the denominator x squared plus 5 quantity squared, I will get 2x to the third plus 10x minus 2x to the third, and those 2x to the thirds will cancel out. So my derivative will be 10x divided by x squared plus 5 quantity squared. Okay, now I'm going to do a first derivative test, so that means I need to figure out where are my fence posts. So that happens at critical numbers, and what are the critical numbers of this function? Well, the denominator is defined everywhere, so there's nowhere the derivative does not exist. But the derivative is equal to 0 when x is equal to 0, because I would plug in 0 and I would get 0 in that numerator. So I actually only have a fence post at 0. So let's test x equals -1. And notice that my denominator is something being squared, so that's always positive. So I really am just concerned with that numerator. If I plug in -1, I'm going to get a negative. This is a first derivative, so that means it's decreasing. For my next interval, let's try x equals +1. And if I plug that into my derivative, I get a positive, which means my function is increasing. So we go from negative to positive. That means 0 is going to be a minimum. Okay, so what is the interval that my function is increasing on? That would be 0 to infinity. What is the interval that my function is decreasing on? That would be negative infinity to 0. And where do I have a maximum? I actually don't have one, so none. To have a max, I would need to change from increasing to decreasing, plus to minus for the derivative. Okay, where do I have a minimum? I have a minimum at 0 because my derivative goes from negative to positive. My function goes from decreasing to increasing. And how do I find the y value of the minimum? Well, I would plug it into the original function, and when I do that, I get 0. Okay, so there's increasing, decreasing, max, mins. Now I need to figure out where is it concave up, where is it concave down, and do I have any inflection points? So to do that, I will need to use the second derivative test. So I need to find the second derivative. Let me just rewrite my first derivative here. 10x over the quantity x squared plus 5 squared. And I'm going to have to do another quotient rule. So derivative of that top is 10. I have to use chain rule in the denominator. So I will bring down the 2, and then I'll have an x squared plus 5, but I have to multiply by the derivative of the inside, which is 2x. So I get 4x times x squared plus 5. All right, let's come over here. F double prime of x, low d high, well, that's going to be 10 times x squared plus 5 quantity squared, minus high times d low, 10x times 4x times x squared plus 5, all over low squared, x squared plus 5. When I square a square, I will get a power of 4. Okay, so we have looked at how to handle derivatives like this. Instead of multiplying everything out, we notice that there's an x squared plus 5 in every factor. So let's cancel it out. This entire factor goes away. This squared becomes a 1. This to the 4th becomes a 3. So I get f double prime of x equals, now that 10 and the x squared plus 5, since there's just one of them, I can multiply those. I get 10x squared plus 50. And the 10x and 4x will be a minus 40x squared, all over x squared plus 5 to a power of 3. And then let's just do a little bit of simplifying. Keep the denominator the same. The 10x squared minus 40x squared, let's see, I'll have the 50 there, I'll have a minus 30x squared. All right, so now we need to find those fence posts for our second derivative test. So again, is there anywhere this derivative does not exist? No, because our denominator is going to always exist because of the x squared plus 5. But it looks like I have 2 fence posts from the numerator equaling 0. That would be if I set that numerator equal to 0, I'm going to have a plus or minus square root of 5/3. So let's put negative square root of 5/3 here, positive square root of 5/3 here. And to get an idea of what the square root of 5/3 is, we can plug that into our calculator. And it's about 1.3. So let's test -2. So again, my denominator in my second derivative is always positive because of the x squared plus 5. So I really just care about the numerator. If I plug into my second derivative -2, 50 minus 30 times -2 squared, I'm going to get a negative number, which means my graph is concave down. Okay, for my next interval, let's test 0. That's an easy one to test. If I plug that in, I get a positive, which means my graph is concave up. And then if I plug in x equals 2 for that third interval, that's going to give me the same thing as the -2 did since it's being squared, so it's going to be negative concave down. So back up here, my interval where my graph is concave up is between the negative square root of that 5/3 and the positive square root of 5/3. And it's concave down from negative infinity to negative root 5/3 union positive root 5/3 to infinity. And then I actually have two inflection points, so I'm going to take this inflection point and write it down here. I have concavity changing at both of those fence posts. So I have one at negative root 5/3 and then one at positive root 5/3. And these are points on my graph, so to get the y value, I need to plug them back into my original. And if I do that for the negative 5/3, I get, looks like exactly 1/4. And then if I plug in the positive square root of 5/3, it looks like also get exactly 1/4. All right. So this is everything I need to graph. And I've got some smaller numbers here. So I think actually my y-axis I will scale by 1/4. And I'll keep the x at 1. So what did we have? We had a y-intercept at 0, 0. And remember, we have a horizontal asymptote at 1. So that means in the long run, our graph will level out there at 1. X-intercept was just also 0, 0. The min was 0, 0. So the only other points we have are these inflection points. So the negative root 5/3, which remember was about 1.3. So maybe about there is up at 1/4. Same thing for the positive root 5/3. So we're going to have those points as well. So our graph is decreasing up until 0 and then increasing from there. And it is concave down until the inflection point. So something like this. It is concave up between the two inflection points. And then it is concave down again. So our graph will look something like this. And I know it's leveling out there at 1 because that was where my horizontal asymptote was. And I knew that it was decreasing up until 0, and then 0 was a minimum, and then it was increasing from there.